This one. Right. It's not as fun. Like, should I just leave these pens here so people know that pens are better? I'm gonna leave these ones here and maybe
Someone else can know as well.
assume they must. I mean, I know David comes here afterwards to do a session.
Yeah,
I don't know. Yeah.
Backboard is whiteboard.
Yeah.
Was a community college and never used backboards.
Really?
Yeah.
Oh yeah. Let's see, what did we want to do today? I'm flying through this material. I want to make sure that y'all are getting out of it what I need you to, but know what these are? Not Rolando. Anyone but Rolando. Capacitor and a dipole. Yeah, very good. Are they the same? No, and you've already done the homework, right?
Mhm.
You looked at the homework. You started the homework.
Yeah.
You're like 80% done.
Mhm.
You know it's due on Tuesday.
Yeah.
Okay. That's why you did all the homework. That's why you have no more questions. You didn't come off stars. I still have questions because I didn't do the homework. Okay. So this will be important because if it looks like a duck and it talks like a duck, is it a duck? It's a goose. It could be a goose. You never know, but it's definitely not a horse, right? Horse, duck. And if you don't know what I mean, you'll know what I mean when you know. Okay. You ready? Question before we start? All right, we're going to talk about fields and dielectrics. Okay. That's not how you spell it. Okay. You're going to see some stuff today that's going to make everything make a lot more sense, and then it's going to become more confusing. Okay. So typically, when we do physics, we think about the spherical cow, right? You've heard this analogy before. So you approximate a cow as a sphere, and then you do all this math on it. And then at some point in real life, you approximate the cow as a cylinder with a bunch of smaller cylinders, and then eventually you have to model a real cow. So we're moving towards modeling a real cow, because for the most part, we've talked about items existing in a vacuum, and we don't do that type of science. Even when you're in space, you don't do that type of science, right? Okay. So let's assume that a material has a polarization per volume, big P. Okay. You can calculate the potential, I hope. So the big P gives you something like this, 1/4 pi. Sorry, the potential looks something like this. And we're just gonna make sure that we understand a few of these words here. Right? What's this one? What's that? Yeah, epsilon what?
Permittivity.
Permittivity of free space. Hold on to those words for a second. Permittivity of free space. What's this?
Is that the effective volume charge?
The effective volume charge, or another word that the B, the bound charge, right? Good. Okay. Good. All right, so we understand everything. And so we can write the bound charge like this. Rewrite the bound charge? Where does bound charge come from?
Oh, it comes from the divergence of the,
Of the what? Of the dipole moment?
oh, wait. Oh, wait.
Of the polarization of the material, right? It's this big P. So this is the dipole moment. Per unit volume. Really should be polarization per unit volume, but we're using P too much. So I'm trying to say dipole polarization per unit volume. Okay, so then it's big P, right? And these are that, and what's this? Sigma B?
Oh, bound surface, effective bound surface.
Right? And how do I write that?
That is,
What's that?
Something dotted with the
Something dotted with N, good, I like that.
R.
Close. P dotted with N. Okay, how much of it's coming through the surface? Right, surface charge. Okay. So this tells us something that we haven't really been thinking about, but now we'll have to think about. This piece here is bound charge due to polarization. The divergence of the polarization creates bound charge. So in the absence of polarization, you have no bound charge. Okay. But some dielectrics will have charge densities already. So we will have to write something like this. Okay, the total charge density is the charge density due to the bound charge plus everything else. Let's see, the free charge. So this is all other charge. And this is bound. Okay. That seems straightforward. Right? Okay. But now we need to define E. Okay. E is going to be the total charge. And what's del dot E according to Maxwell's law? Rho epsilon. Right? But it's this one, right? So this is really the bound charge plus the free charge times epsilon naught. Okay? And we're going to make a new word, a new phrase. And that's going to be the electric displacement D. So what does that mean? Electric displacement is epsilon naught E plus the polarization in the material itself. Okay, and this will simplify the above equation to simply this. Okay. Okay. That seems like mathematical mumbo jumbo, and in fact, in some ways it is. But what we're trying to do is we're trying to link together where the sources of various electric fields are coming from. Okay. Questions about this before we jump into how this is going to work in practice? Okay. So in linear dielectrics, you're mostly going to say that P is proportional to E. Oh God, that's too many. Oh, whatever. That kind of works, right? If E is not too big. Generally speaking, we say something along the lines that P is equal to epsilon naught this. And you might have seen that similarly before, but it was like an alpha. It's really this thing here, the permittivity of free space multiplied by another thing, which is called the susceptibility. Susceptibility. Long one. So what's the susceptibility? Well, the susceptibility is just like how likely you are to become polarized. So if we're thinking about people watching Fox News, right? How likely are they to be swayed by the argument on the television? That would be the susceptibility of, say, your grandmother, right? As opposed to in a material itself, due to an outside influence, like an electric field, how likely is that material going to change its orientation? Susceptibility of the material itself. Similar, right? Okay. So we can clarify this more. We can say that the D is equal to epsilon naught E plus the polarization. Okay. And we can redefine this one so that we can say epsilon naught 1 plus this here is going to be epsilon. Okay. So before we said the epsilon was the permittivity of free space. And now we realize that in a dielectric, inside of a material, it's not free space. So we drop the naught. And we just say the permittivity. Right? Yeah.
Is the gamma, is that the same thing as an X? You know,
Oh, sorry. Yeah, this is not a. It's that. You write that better. I definitely did my gamma, but I did not mean to. Okay. So in this case, what we're doing is we're trying to draw this analogy between empty space and space with stuff in it. Because generally speaking, I showed you that picture of the capacitor early on. There's never nothing in between it. What's in between it? There's two plates.
Oh, the capacitor is
Air. What is air? Is air a conductor, a dielectric? It's a dielectric. It's a, right? It can break down and become a conductor when it becomes ionized. But generally speaking, it's a dielectric, right? Because that's the reason why you don't get shocked by something sparking. It's over there. Water. Conductor, good. Okay, that's the difference. You will get shocked if you drop, you know, say a toaster into your bath. Right? That's the canonical example. Okay. So here we're seeing that the displacement here is due to something, the permittivity times the E field. Okay, and we're gonna work out what the hell is going on here. So let's look at this example. What's that? Yeah.
Sorry, to kind of a little backtrack, what is the D vector again? What was the definition for it? Oh, like what is the actual word for it?
Displacement. Let me write it. Okay. And we're gonna see that that has an intuitive meaning in a few seconds. Okay. So what's this? What have I built? Capacitor, yeah, I just said that, right? Okay, we're just paying attention. So we have a plus up here and a minus down here. These are free charges, right? Okay, how does the E field look?
The positive one to the negative one.
Straight down. Is that fair? Let's write that like this. Good. I'm also gonna write that the D naught is straight down. Is that reasonable? Oh yeah, because I'm, you know, making the rules up here, and I said E naught was straight down, and I just multiplied it by a number. So D naught has to be straight down, right? Okay. So let's look at this in the context here. So we say something along the lines of what is the strength of E naught? Well, it's the bound, or sorry, it's the free charge over epsilon. And you'll see why I'm using these knots in a few seconds, because currently there's nothing in this. D naught is just E naught times epsilon naught plus 0, because there is no polarization yet. And that's the mount charge. Or sorry, the free charge, right? Okay. So now let's make it real. Okay. So now what's gonna happen? Let's say there's even a little bit of polarizability in this material. Intellectually, what are we thinking about?
What are those lines?
Stuff, something. Material. Empty? Space? Vacuum? Not vacuum. So I put a dielectric in here. Okay, this stays constant. So we keep the charge here on this plate and the charge on this plate constant. In fact, when you look at a capacitor that you are using in a lab, right? It's not two plates and an empty space in between. Because if you move it around and one of them touches the other, you've ruined your capacitor. So what you'll do when you build any capacitor in real life is you will put another material in between, and they will all be touching. Right? Makes it more robust. So in practice, you'll always have this situation, right? Because you're not doing space. Okay. So I put some material in here. Let's assume that it can be polarized at all, even just a little bit. Now let's think physically about what we're going to have happen. Do we still have an electric field going down? Yes, we still would probably have this situation. Talks like a duck, walks like a duck, probably duck, right?
Mm-hmm.
But that's going to cause something to happen in this material.
When it become polarized, because it's going to an electric field.
Right. So now we took something that can be polarized and we put it in an electric field. So now we expect polarization, right? Okay. So in here, how would this polarize? What would the distribution of charges look like? Go over here for a second. Which way would the polarization go? Oh shoot, I forgot all these things, right? What is P?
That would go back to one.
Yeah, that's the individual one, but if I'm thinking generally speaking, how is this proportional? Yeah, it's proportional to the field, right? Okay. And they go in the same direction because they're vector identities, right?
Okay.
Okay, so let's assume that the polarization here goes in the same direction as the field.
That's what probably negative.
So I have positive up here, so negative down here,
Mhm.
and so the field's going that way, and the polarization's going that way. So how do the charge distribute themselves? If there are any.
Oh, the negative, what you said, negative, like towards the top plate.
Ah, the negative charges collect near the top plate. And the positives collect near the bottom plate. This is exactly the same number of positives and negatives. And I'm really good at drawing, right? Okay, so let's draw this in the direction. Down, 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 down. And you saw that before. You saw that in the material, right? You get an effective bound charge due to polarization. But now we're thinking about two things simultaneously. We're thinking about the free charge on the capacitor inside of a dielectric, which then orients itself such that it creates bound charge here at the surface. And that effectively will do what? Magnet. Not a magnet, but we're not yet looking at magnetic fields. Let's not confuse ourselves. We're just looking at what happens when I create more charge here that's positive next to this negative charge. It'll start to cancel, right? So it'll be reducing the free charge because I need to consider at every location the bound charge and the free charge, which is what I said over here. Electric fields are generated by the presence of charge. And if I add together bound charge and free charge, this will change what my electric field is. Yes or no? Okay. Because in here, I could say, well, what's the E field? Right? What's the E field in this location? Is it bigger, smaller, or the same as it was here? Smaller. We see that yet? Wait, where is it smaller? Good question. Kobe, where's the smaller?
Bottom.
So
Why is
electric
it small?
field smaller on the bottom one?
Yeah, why?
Because there's not much free charge.
Right.
Canceling out the inside, right?
Yeah, well, at the bottom, not inside.
Bottom, yeah.
Inside, we don't care about the inside, right? There's still an E field going through it because it's a polarizable material, it's a dielectric, not a conductor. If I put a conductor in here, does this make any sense? No, it's garbage, right? All the charge goes to the outside. Okay, it's only for dielectrics. Good? Okay, intellectually, this is what's happening. Once we understand it intellectually, then we can attack the math. Okay, I'm gonna get rid of all this. We're recording. All right. So what's the new E? Is it knowable?
Yeah,
I hope so, right?
and we go back to the first equation.
What was the first equation?
The one that we used as a divergence to E field, which is equal to the charge density times epsilon naught. But then we expanded it to adding the bound charge density and free charge density times epsilon naught.
Yeah, I like that. I'll go even a step further. I don't want to use epsilon knots anymore because we're
yeah.
no longer in free space. So boom, we'll just do that, right? Okay. So that means I can write it like this. So epsilon or E is equal to D over epsilon. Okay. And what was D before? I could write it like this, actually. I'm gonna do 2 steps here just to write it out to you pedantically. Okay, I know that's annoying, but don't worry about it. So it's sigma free charge over epsilon naught. Okay. This will be 1 in free space and otherwise not for the material. Okay, that's the permissivity of the material itself. Okay, so E, the new E is the old E, epsilon naught, divided by the new permissivity. Small, just like this. Now we see it. Okay. You can also say this, just to rewrite this on the board. Maybe I'll write it up here. Epsilon naught E plus P. That's okay, right? Let's simplify this P a little bit in terms of our new language. Okay, so this was our alpha from before. We're just throwing tons of letters at you. See if you can keep up with all the letters, right? All I really care about in the back of my mind, I don't give a shit about the letters. I give a shit about the relationships. Polarizability is proportional to the E field and it goes in the same direction. The displacement is proportional to the electric field and it goes in the same direction. We already knew that it would go in the same direction as the polarization because the polarization is tied to the E field. They're all tied to one another. There's 3 different ways of looking at the same phenomenon, right? Well, they happen, whatever. Okay, so let's map this out. Okay. We're almost there. That doesn't matter. This matters. Polarization is the difference between the original electric field and the one that you end up with. Or another way to rearrange this is that E is equal to your original electric field minus the polarization. Is that reasonable? Does that fit our expectation? So we've seen this before and we didn't really appreciate it when it's happening. You had some sphere with polarization vectors going through it. Right? And we said, what's the E field inside of the sphere? I write it like this. Here's the sphere, here's the polarization vector P, and they're uniform and they're going up. What's the E field? Wasn't it? Yeah, but inside. You're right. Absolutely right. Inside, outside was looping. Inside it was
It's like here, same direction.
same direction,
Oh,
opposite
yeah,
direction inside. And so we kind of just went by that, and I said, well, just don't really think that hard on it. Right? Look over here for a second. Imagine that you didn't have the capacitor. Okay, let's get rid of the capacitor, keep the dielectric, and keep the bound surface charge. What would it look like, the E field inside? It would go up. And we know these E fields can just stack, they can just add, right? So polarization going in the same direction as the external magnetic field or the external electric field sets up, right, a charge distribution that goes in the opposite direction of the original electric field. Same example, right? I mean, not the same example, same process. You see that?
Can you explain that one more time?
Yeah. Okay, starting with nothing. We're gonna walk through this whole process. Starting with nothing, just charge minus here, charge plus here, electric field. Okay. This one here, I put a thing in, something, air, sand, I don't care. Something goes in here. Now line themselves such that positive is down here and negative is up here. If I somehow had that material with that bound surface charge, ignoring the fact that it's a polarized medium, just looking at this medium and ignoring the parallel plates, I would say, oh, this would build an E field that goes in the opposite direction. And so this E field, new, and this E field, old, would be added together in this region here, and it would be less.
Why are we thinking about that?
Because this is how all materials in life really work. We do not have free space. Right? Anytime that you're putting current through something, more often than not, you're hoping that it's a good conductor, but it's not a perfect conductor. Right? Your capacitors, they never have air. They only ever have something in between, unless you're working on a rock paper scissors. Does that make sense? Intellectually, this makes sense? Okay. I think I've said this. Let's talk about the key points. This piece here, the polarization, multiplying by these two things, which are numbers, is a result of the final E field. Okay. So E naught induces D, creates D, which changes E, right? such that the final E and P are related. Okay, does this go back and forth forever? That you can never solve the problem? No, no, it's gonna be okay. We can solve this one, right? We just showed how much it decreases by. It's straightforward, as long as you understand the polarization of the material itself, right? Okay. And this is true for linear dielectrics. I said linear, this is because this is the way that they are acting. Notice that the property of E is linear. If you had E squared, you'd be really scared. We don't have that. For the most part, you won't deal with linear dielectrics in your normal life. Grad school, probably. And then you'll have to use susceptibility tensors in week 7. Okay. We wrote that piece. Okay, that's good. Good at permittivity. Okay. Generally speaking, I guess I should have written this here. These things are the same. This is the definition of the permittivity. Is that fine? Let's look at this example one more time just to make sure everyone gets there. I want you to draw for yourself where the bound charge is using. I didn't know it, but you know what it is, right? How would I draw the B? The bound charge. Negative on the bottom. A whole way? A fourth of it. Okay. How are we making these guesses? Is this just vibes?
That's the normal around the perimeter of the circle.
The normal, we're dotting it with the normal, that's why I wrote it.
So
So the place where the bound charge will be the largest is
like right at like the vertical axis.
at the vertical axis. There'll be minus here, big minus, big plus.
And then, like,
Is there a charge here? No bound charge there.
No.
Okay, what do I hear? Beta minus. Here. And it's changing by the amount. Cosente, no?
Yeah.
Okay. Here, little bigger, little bigger. We'll assume that that's perfect. Okay. And now we connect the field lines. You see in your mind how you connect the field lines? Inside. You're right, but inside. Here there's nothing. Okay. Do they do this? Raise your hand for doing this. For the electric field inside. Okay. Raise your hand for. This. No, why do you not like that one? You like the other one? Yeah, okay, so we forgot that there's charge on this side, that's because I didn't draw it good. Does this change your answer at all?
Yeah.
Oh, okay, you knew that it would be on both sides, so you were just like filling it in your brain. Okay, so could it possibly be this? Well, no, because then it would have to be balanced by this side, right?
Yeah.
Okay, so you have a symmetry here, and you see in the problem when you have the symmetry that you're gonna need to connect these lines with straight lines. Because it's centered here. Right? You can't have this guy going that's crossing. Right? And you can see that in the actual derivation, which you did, right? I know that when you go home, the first thing you do is you open up that book. I'm gonna do these derivations we did in class. Right? Okay. All right, so let me ask you a different question. Here's E going down. Okay. Let's think about the different components here. E perpendicular at A, top here, minus E perpendicular at B is sigma over epsilon naught. Whereas the parallel components are 0. That's okay. Let's talk about D. D is that linear combination of these two. So outside here, we're gonna think about on the inside and outside. Okay, so here's E. Let's do this properly. Here's P. And then we'll assume that outside there is some E2, right? Some other E. Okay. Here's EA. Here's EB. Okay. Outside, what's the displacement? Why would it be 0? Is there a field? Well, think about there's still the charge distribution, right, on this sphere. There's positives and negative charges on the surface of that sphere, right? So there's loop-de-loops, right? So even though we haven't drawn it on there, I know that there is a field. But now I just want to compare it to the displacement vector, which I wrote up there, right? And I want to connect the displacement vector in both of these locations. Ask your friend.
Why was it equal to 0?
Which one?
EA minus EB. B is outside, A is inside, right?
Yeah, well, I wrote A is inside and B is outside. I'm just saying here they need to connect. This is a continuity problem.
Oh,
Right, so these pieces here are needs to be smooth. Can't have an electric field that goes to the surface and then goes off to whatever.
like there's a conservation, basically, of the field inside and outside.
Not necessarily conservation of the field. What I'm trying to say is that the field lines themselves are smooth. Right. Approximation more or less. But this displacement vector outside where EB exists must be equal to here's the displacement. The displacement depends on epsilon is not a thing it depends on. That's just a thing, right? The electric field and the Polarization. It's okay, there's lots of words. I'm not gonna give you any points off for using the slightly different word of the same third thing that we use P for, right? It's the right idea. So polarization and the electric field give you the displacement. Okay. Outside of the sphere,
We have to use,
what is the displacement?
we have to use epsilon naught?
Is it just? Why? There's no polarization outside of the sphere. Okay, so that's good. So then we know D outside. Whew, easy.
Can you explain conceptually what D means?
So you have the electric field. The electric field creates polarization. The polarization affects the electric field and changes it. It displaces the electric field. Right, so we saw this example of the parallel plate capacitors. Okay, changing charge, which changes the E field. So you start with an E field, right? And because you have real materials in the world, you end up with something different.
That was the part that you were saying, like there's positives, negatives on the inside.
On the inside that are
Outside edges.
canceling out a little bit.
That cancels out kind of the other
Yeah.
one. Oh,
It reduces it, right, slightly.
Yeah.
And you can see how much it reduces by this. Right, this is what you're left over with. Here's what you started with, right, in free space. Here's the polarizability of the material, and here's what you have. So no matter what you get, if P is anything other than 0, this is not gonna be equal to that. Right? Maybe I'll do this.
Concerning the displacement outside, we're using the displacement equation when we have to use like epsilon naught. So wouldn't like the displacement be epsilon naught times TB because
Very
it's free space vector?
That's right. That's called being correct. This is called being sloppy. I'm okay with both. Okay. All right, what about inside? What? What's that? Right? Straightforward. Now we get it. Plus P, okay, good. There we go. Good. So this isn't, I'm not saying this is intuitive, I'm not saying this is gonna be easy. But we need to, you would do the same thing with the Ds, you connect them, you have the surface charge, right? And you'd be able to see that this surface charge, when we put these ones in here, you're gonna get rid of that E naught, and then you'll have a delta P from the top to the bottom. It's okay. Can we figure out, now that we have these E's, we figure out the potential that's everywhere? We care about that. If I have E everywhere, and I get the potential.
Oh yeah, we could just take the negative divergence.
The negative divergence,
Wait, no, I thought, wait, my bad.
the potential V from E. Wrong operation. Let's think about them physically for a second. Potentials are forms of energy. Electric fields are fields of force. What is the operation that connects from force to energy? What? Integral. The integral connects those, right? The derivative of the energy is the force, and the integral of the force is the energy. That may not be intuitive, but you'll have to pound that in. Okay. Isn't that one? Okay, and then we have something that's straightforward. So EA is not a given, hopefully it goes right later. We're not gonna focus too much on that. We could go through and we could do this derivation, but the important thing here is remembering this piece. Okay, if you can get to an electric field, then you can integrate it, hopefully if the geometry is good. If I fucked you and then I gave you something that the geometry is awful, and you stick it into Wolfram Alpha, and I'm like, good job, right? Or because you have computation already, you do that integration with your computer. Right? In practice, sometimes you're yeah, you use Runge-Kutta or you use the trapezoidal rule, you can do the integration without ever solving it. Fair? Okay. Let's try something new. See if we can do a problem from the homework. I know this is a lot of like words, so I'm trying to like break it up. Oh. I forgot. But I do wear these a lot in the summer anyway. Okay, folks. For 13 in the book. A very long cylinder. You've seen these before. Radius A. There is a uniform polarization P perpendicular to the axis. Find the E field inside the cylinder. Yeah, yeah, okay, careful, it says uniform not. That makes sense? Okay,
Well, like it's not. Like from center, right? That's what you mean, like, not radial? It's not expanding out from the second.
like that.
That was that. Right. Like if this is the cylinder, it's not going on like this.
Yeah,
Yeah.
yeah, it's not radial.
Oh,
It's only gonna,
What's this? There.
it's like that.
But it's this,
yeah, if you were to take it like as a side view, it probably looks like a sphere right behind.
perhaps.
Yeah.
I want you to think about it. And it's on this recording. By the way.
It's something like this side. of the- Oh,
What?
Isn't it just like that one?
You tell me?
I think it would.
It would be.
That's what I'm doing.
Right.
Okay, let's think about how we do homework problems, okay? Let's say we make an assumption. Okay, we write that assumption down and we do the problem based on that assumption. And then I look at your work and I say, oh, he made the wrong assumption at the beginning. He chose the wrong direction. But look at all the math he did, that's correct. That's why we write our thinking down. So that we can get the credit that we deserve. So if you interpreted this as radiant, let's say you missed this word radiant, right? And you did the polarization like that. And then you did the whole problem. And you did it right. Good job, 100%. Bad reading, good job, right? So you choose, you say, oh, I think it looks exactly like that, and I'm confident in my interpretation. I don't need to ask in order to figure it out because I'm gonna move forward as though that's correct. Good job. Right? You might be right. But part of this is interpreting the problem and knowing where to go, right? That's the self-efficacy of like getting yourself into the problem in the first place. So, well, hope this is right. I'm gonna write an explanation, right? So we're writing words in class and not just P equals.
Sorry. Literally.
What is epsilon now? Permittivity of free space. And then this is the permittivity. And that's the material.
Oh.
That's gonna change. I mean, they're all based, right? This is based on emptiness. And these are based on material. They're just multiplied. You done?
No.
Well, talk to your friend, right? You're setting up the problem, you're comparing with your friend. You're completely stuck. You've already started talking to them and being like, yo, what the? Doesn't make any sense?
right? You said we can choose.
I did?
Yeah, I think, yeah, I think he asked if we could choose which way it went.
You were arguing, right? I want you to argue. You don't have to ask me, right? You're almost a graduate of physics. So you make an argument, you hold true to that argument, you say, I choose the key in this one. And then you do the math and I go, wow, he understood it. Right?
I did too, and I wasn't going up, just so you know. Keep going, yeah, so it should be like, well, it's gone now, but yeah, like that. And then. Because down.
So my question is, does the find the E inside the cylinder?
Yeah, it's electric field.
How did I know that the E field went down there? Were there other steps? Is there anything I did? Right, that's the question.
Now. Yeah. Yeah, we can show it inside. I see. Are we supposed to like? Set up on the electric field, explain why we think I should do that a certain way.
Yeah, I mean, I wanna see your argument for why the election field is a certain way.
So that's what I did, I just don't have to.
That means that the.
Okay, well, what's your argument?
Why is it? I said the key goes to the right. So now all key goes to the x-axis. And so there's the negative charge will be left.
Okay.
Positive will be right.
Okay.
So electric field go positive.
I'm good.
Okay.
Oh, you.
Does it matter that it's a long wire?
No,
It doesn't matter.
I don't think so.
Has the same figure.
Yeah, maybe it does.
I don't know, you tell me, right? This is all the things we need to think about. Is a sphere the same as a wire?
It's just really small.
A sphere is the same as a wire.
The wire's really tight.
Right, so that's why I said that L is much longer than A. Is there any input from the fact that there's a long wire? That's my argument. I wanna see you thinking of all these different things. We talked about what's the difference between, right from the home, we have this problem. Are these the same thing? I want you thinking not just, oh, okay, this looks exactly like this and therefore it's the same. What are the things to consider and have I considered them appropriately? What is the wire? What does the electric field in a wire look like? Is there an electric field in a wire with charge on the top and the bottom?
It doesn't matter how long it is.
It doesn't matter how long it is, so what's the argument?
The argument is that it's uniform, the polarization is uniform throughout the entire wire, regardless of how long it is.
Yeah.
So it's gonna be the same if you look at a cross section.
See the argument? Huh?
The length is not.
It's not that it's a circle, the circle look right, no, you need an argument.
Why did you do it from left to right?
You can argue it however you want, don't get mad at him.
That's gross.
No, don't get mad at him, it's okay.
He said from left to right. Where are you at? Here you put the charges on the outside, it was the cross section. Put the charges on the outside of the cross section. You
Oh, starting with the polarization.
Negative, it's a little, it's a.
where the positive.
Already.
You're. Oh, you're doing it that. That should not perpendicular to the axis, though.
It's permitted with x-axis.
They never specify what axis it is.
That should be the house.
I guess it doesn't matter, but it's just, I would have thought about it, to put it that way, from left to right. We didn't specify.
What?
Specification of which axis.
Well, it's not radial,
We just pick.
that's what the word is, not radial means. What?
We just pick the axes.
Because it says.
Why are you choosing an X, Y, and Z coordinate system with a radial coordinate?
Not radial.
Alright, no, but that's what I mean, you have a cylinder, so why not choose cylindrical coordinates?
You want to do perpendicular to the equal.
Yeah.
It's not radial, that's all I'm asking. Right? P does not.
You just not really make
Ah,
taxes.
Does one not, or how long it is? It's beautiful polarization. Long the entire. Small cross section or a large cross section.
Yeah.
Because it's uniform throughout the whole thing, you don't have to examine the entire thing, just sliver. Cause it's the same thing.
Yeah, then it must be like, if PHYS is cool.
I like.
Yeah, but.
Yeah.
Well, hold on, I mean, have you done it? What's the E? It's not just the thought experiment, it's not gonna be the exact picture that you saw before.
We used to del dot E.
How would you find the E field inside? A long cylinder. So before we had a potential for a sphere, we just figured that out because we had the potential, we could integrate, we could get, or we could do the derivative, we could get the E field, right?
Yeah.
So is there any other techniques that we can use here?
Well, I guess, what I did was, we know the polarization, so we know this charge is on the outside.
Okay.
Yeah, and when you know the charges, how they're oriented, you know which way the field is going based on the charges.
Okay, but how do you quantify that? Is there any way you quantify that?
If we don't have numbers.
I mean, I like starting with that picture, right? Because that gives us in the back of my mind what I know I should intuitively end up with. But then I need to use math.
Yeah. There's no numbers.
Why do you need numbers? Math is not numbers, math is letters. How do I find the E field, say, inside of a uniformly charged wire? Oh, Gauss's law. Very good. Trying to make me eat myself off a bridge this morning.
You remember Dawson? We're like, we made a shape around the thing.
Alright, let's do that.
Here we got like cylinders inside of cylinders, like. All the time. Yeah.
In-
Kind of boxes. Okay. You know it.
If I look at all of them.
Yeah.
No, we don't.
Let's imagine inside here at a distance R, where R is less than A. That's what the question is asking you. Can you find an electric field? That's the question, right? You're doing this intellectually, but you also want to know how to solve these real problems. You go to take the GREs, you're like vibes as the answer, not gonna work, right? I don't know, like down, I guess, left if you want it left. No, there's a real answer, right? And you can calculate it.
Is it negative, del dot E?
E.
Isn't that was like the bound charge?
That's the bound charge, right?
Yeah. The divergence one.
So let's say there is a volume charge.
Okay.
Right? How would you solve this problem if there was a volume charge? Someone already said it.
He said. That's.
Right, why is that reasonable?
Is Gauss's law del dot E equal to rho epsilon?
Yeah, but there's an integral formalism that's better, right? Right. Yeah, the integral of the closed surface is the
It would be.
Q enclosed.
Yeah.
Right? Wouldn't that be the way that we attack the problem at some random arbitrary distance inside the sphere? How much charge is in there? Well, let's find out.
Oh,
Because we're talking now, for example, about some distribution of charges left and right. Maybe that's how they're oriented. How do we find the E field inside of it? As a function of distance.
Function of distance?
Yeah.
Yeah. Well, Gaussian surfaces don't take this, okay? Or.
What?
I don't know.
Outside, you know what the E field looks like, right? Then you just have charge on the outside. We're completely lost here. How are we feeling? Feel like there's a lot less talking.
Maybe it was less.
So we're. Say anything about the instance where you're explaining something while you're saying it?
We should consider. How do you create the E field inside of a cylinder of uniform charge density? That was my hint to you. And someone said Gauss's, and I said, correct. We can use Gauss's law, we can create the E field as a function of distance. One way we could think about this, right? Let's say there's polarization, individual atoms that are separating, maybe you have a positive and a negative charge. So you could consider, if you wanted to, that you had two cylinders. One which is a positive cylinder, and one which is a negative cylinder. And the resulting E field would be, well, it can't be zero, right? There's bound charges. But you would add them, because they're vector quantities. So you have the contribution from all the positive charges, as though you have one cylinder, which has a positive charge, sitting on top of a cylinder with negative charge. And the separation between them, of course, will be your dipole moment. Right?
Isn't that radially though? Like, if you do it like that, go cylinder and then cylinder.
Well, the way to think about it is like you have two cylinders like this, right? And they just happen to be sitting right on top of each other. Maybe they're just slightly displaced in the direction of the polarization vector, right? Because the polarization tends to be something like QD for an individual atom. And that direction is the direction of the dipole moment of the individual atoms, right? Okay, let's go back to the very, the conception of how we think about these types of problems. Inside of the material, positive, negative, some distance d. That's the definition of a dipole. It has an orientation, right? Okay. I have some object here. We chose left to right, right? Or you chose up, down, I don't care. You have some polarization direction. So inside all of the individual atoms, all the positive atoms are displaced from all the negative atoms. That's not the right way to say it, but you get the idea, right? So conceptually, I can think of how do I get the E field from an individual rod of all the positives? That's Gauss's law. What if I had a rod that was just full of positive charges? I could get that, right? Symmetrical, cylindrical, some distance, enclosed charge, bada bing, bada boom, right? Now I add them. Positives and the negatives. And D is their distance. Dipole moment, part of the polarization. No or yes? Everyone hates that? Don't like the vibes? Yeah. Good. So do dipoles cancel? No. They don't. They're existing in nature, right? So here I have the positive and the negative charge. Let's draw a circle around it. Right? Q enclosed could be 0. There's no E field, right? There is E field inside, right? Go out and then back in. All right, so are you asking like, how do we ever get E fields? No. The fact that they're separated, the fact that they're not the same part gives you a contribution of E, right? Think about if these were highly polarizable objects, the positives and the negatives were very far away from each other, then the E field would be proportional to the polarization, right? As opposed to thinking, well, if there's no polarization at all, they don't separate, positive and negative sit right on top of each other, then you're right, absolutely cancel. But the fact that there is separation is what creates the difference in the charge, right? That make more sense? Anyone upset? Anyone wanna cry? This is still reasonable, just annoying. Reasonable,
That is,
annoying. Checked out. Alright. I shouldn't have asked that one. Okay. There's another part to this problem, and so this is one that you'll do in the homework, I promise. Now that everyone needs it. And that will be finding the E field outside and showing that it has a specific form. How would you find the E field outside?
would it be the equation, the electric field is equal to, the original electric field minus, polarizability, or polarization over epsilon? Would it be that?
You're thinking along the right terms, you're thinking in terms of the work that we just showed, but actually I'm just trying to make sure that we understand the math for getting Gauss's law and polarization right.
Okay.
So this isn't a new problem, this is a problem much more similar to the homework that you're turning in right now.
Oh, so you probably just take the Gaussian law, but like actually like go greater than A, so from like A to infinity.
Bada bing, bada boom, right? And now what's the weird technique that I just taught you that everyone hates? Multiple cylinders. Treat the positives and the negatives as though they're different. Right? That's the trick. I'm trying to ram into your head. Because you know how to do positives and you know how to do negatives. So just do both of them separately.
So kind of like a image problem? I like it where it's like.
I wouldn't go exactly
no,
that far, but yeah, that's the right frame of, thinking about things. We can imagine the world as we want it to be, as long as it mostly represents reality. Questions about this problem? Okay,
Sorry, can we like message you on Slack? That's the thing.
I hope so, yeah. Slack's still there.
Yeah, Slack.
Yeah.
It's still there.
I may not respond all the time, but
That's fair.
you're welcome to always either stop by my office or message me and be like, hey, I don't get the hell what's going on.
Okay.
Okay, I don't have very much time left. But we're gonna say some things that you're gonna hate too. Yeah, go ahead.
So, this one is added to the whole 4.2 and all the homework ones.
No, this is homework 2.
Oh,
Oh, god damn. All right, homework 2, sorry. Yeah,
Where did you find what the last problem is? I thought it was a constant calendar, but it said 1.2 and then just a star.
oh, whoops, okay, I'll update that, that's my fault. That was supposed to already be updated, so that was, I think it's 4.6, right?
Yeah, I think you said.
Yeah. I'll double check, it'll be okay, my bad.
Okay.
But thanks for reminding me, that's important. Okay, let's really quickly write down Maxwell's laws again, especially for the electric field. What are they?
So then. Where the E is equal to roll over and stuff.
And. Okay. That's the claim, right?
It was, before you did like delta E, use rho times epsilon, what's the between this one and that one? If you
Probably wrote it wrong.
Oh.
Yeah. Can't be held accountable for my own action, are you kidding me? This is what we call transcription error, and I'm sure that I've done it before, right? So this is why we had the text, right? The text is like read by a publisher. If I'm writing up here, you saw that I wrote dielectric once with an A, dia instead of di-it. Right? Okay, sometimes what you write down here and you write up there aren't the same. Okay. So this is the case for the electric field, but not necessarily for D plus P. So I'm going to just state this and then we'll basically leave D plus P doesn't have to be 0. There's no reason that D can't have a curl. Okay, and the way that we state this is something like okay. Do we know what this is? Stokes theorem. I think the relationship between this contour integral and the surface. Okay, Stokes, yeah, this is Stokes. The one that you like is Gauss. And that's about the divergence. This one's about the curl. Okay, left hand. So you can imagine a world in which you have two dielectrics next to one another. Let's say that's 1 and 2. And you can follow some path through both of them. Oops. Like that. And as you go through the path, there's no reason to expect that this piece here has to be 0, right? So we're allowed to have curl in our dielectric map. Can't have curl in your E field when it's in free space. Especially when I have multiple materials together, I'm allowed to have curl in my E field. Is that okay? Okay. Sorry that I kept you over, but. Questions, comments, concerns? We'll talk about that more. In nonlinear dielectrics, like I said before, we'll have susceptibility tensors. Thankfully, we're not going to do that.